Step one in building a C compiler is to open the source file. Compared to everything else that I have to do to build a compiler, opening the file seems a very easy task. And it is kind of an easy task. But there's a lot of interesting complexity behind files. And so in this video, I want to have a look at what are files actually. So here's what I've got in mind for this video. I'm going to just talk about the word abstraction and what it means in terms of computers. Then I'm going to talk about what normal users think a file is, how people interact with files when they use a computer. I'll talk a bit about different kinds of files. Then I'll talk about text files and binary files, since those are the two that are the most important to us when we're talking about a compiler. And then I'll talk a little bit about how the Linux operating system views a file. And then finally, I'll write the code just to open our source file in my compiler. Right, so let's get started. The first topic, what is abstraction? Abstraction is a concept that I really like when I'm thinking about computers. I would define abstraction as just simplifying complexity, taking something and providing an interface that's easier to work with. For example, historically, if you wanted cooked food, you'd have to go through the normal process of turning on your stove, mixing up a recipe, putting things in a pot, mixing it just right, letting it cool down, and finally having a meal and then cleaning up afterwards. Whereas nowadays you can buy something that you can just stick in a microwave, press a button, and have a meal. So microwave meals are an abstraction of normal cooking. In programming, we've got abstraction on top of abstraction on top of abstraction. It's layers and layers of complexity simplified to some small extent. And it's pretty incredible to dig down into just how deep that complexity goes. I came across a book called Thinking in C++ about 15 years ago, written by somebody called Bruce Eckel, who's quite an influential and interesting publisher about programming languages. And there's a paragraph about abstraction where he's talking about how C++'s object-oriented approach is a form of abstraction. So let me read it here. All programming languages provide abstractions. It can be argued that the complexity of the problems you're able to solve is directly related to the kind and quality of abstraction. By kind, I mean, what is it that you are abstracting? Assembly language is a small abstraction of the underlying machine. Many so-called imperative languages that followed, such as Fortran, BASIC, and C, were abstractions of the assembly language. These languages are big improvements over assembly language, but their primary abstraction still requires you to think in terms of the structure of the computer, rather than the structure of the problem you are trying to solve. The programmer must establish the association between the machine model in the solution space, which is the place where you're modeling that problem, such as a computer, and the model of the problem that is actually being solved. So basically, my way of interpreting that is programming languages take us further and further away from the nuts and bolts. When computers were first invented, you had to literally put in the ones and zeros to get out a solution, and you had to think in terms of ones and zeros and the operation of the machine. Then came forms of assembly language that helped us have symbols for those ones and zeros and made it a bit easier. Helped us abstract away that nuts and bolts, electrons and transistors thinking of the ones and zeros. But assembly language is still far closer to the thinking of a machine than the thinking of a person. And then gradually we've built up languages and frameworks and tools and everything to gradually get us more and more to the point where we can think like a human and write things like a human would write and still get the machine to do what we want it to do. And in that way, we can even think of the modern large language models as further computer abstractions. This whole series is going to be all about writing compilers, and specifically my journey trying to write my own C compiler, which is going to take me a long time and digging through a lot of complexity in itself. But the whole idea of a compiler is basically this interpreter, this bridge between abstractions. You write a computer program in C or Python or whatever, and your compiler or interpreter takes what you've written and starts to filter it down. If you're producing assembly language or some intermediate bytecode or whatever your compiler is, it's this bridge. Compilers are bridges between levels of abstraction. Maybe it's just me, and probably Bruce Eckel, who wrote that book. But I think it's kind of a cool concept. And it kind of makes me think about the different approaches that I find with programmers that I know. Some people are far more eager to solve the issue, solve the problem. And certainly in my day-to-day work, that's often how I am. I'll go for the most efficient solution, which is, often using some tool as a deep abstraction from the lower level machine. But on the other hand, I kind of want to know what the nuts and bolts are. I want to dig deeper into the machine, understand how computers work down to the basic level. And so that's the appeal of doing something like writing a compiler, to get to know, what did abstraction give us, and what's the underlying mechanics. And there's a lot of it, so it's an interesting and very wide thing to dig into. So now that we've talked about a word a bit philosophically, let's talk about what a file is. So a file is also a type of abstraction. If our computer was just laid out in straight flat memory that we just had ones and zeros all the way through, obviously that would be a very difficult computer to interact with. And so files are an abstraction. In reality, if you go down to the bits and bytes on your hard drive, you're still looking at ones and zeros all the way through. There's no line between one file to another file. The files are abstractions that are created by your operating system. And we'll look at Linux specifically because Linux is open source, and so we can actually see a little bit deeper into the underlying mechanics using Linux, and look at what a file is. But let's start off just by thinking about what files are when you just normally interact with any old computer. So a normal computer user might interact with doc files or XML files or PDF files or images, PNG and JPEG files, HTML files, and if you're a computer programmer, basically text files. All your computer programs are just written in text files. So if we were a normal user on a computer, we would just click on files and open them like that. So if I look at a PDF folder, I can just click it open, and it opens a folder for me. It opens a file for me. I click on a Python file, it opens it for me. I can choose what I want to open it with. VS Code, there's my file. I can open it with just a basic text editor. And there's my file. And that's kind of a normal way of interacting with a file. For many people, they might not even do that. They might just use software that's opening the file automatically, like open Word and then find the file within Word. And that's a very normal way of interacting with opening a file. If I now go into the terminal, we get more into the world of where programmers are typically opening files. And so this is the terminal on my Mac, and I am able to open, can look at the same folder that we just looked at, and I can open the same files with a text editor in my terminal, and I can even open the PDF, and we can see a little bit about what I was talking about before, about abstraction. We can see that a PDF that was a very simple little file when we opened it before is actually a huge amount of complexity that's hidden from us just to interpret what the PDF file should be showing us. So this file is not just the text that was in there, but it's all the information about the colors and the positions and everything about how this file should be shown to the user in the application that they use. If we go over to a Linux machine, I will just sign in to, I'm just SSHing into a different machine, and we can look at files in here. So my files are in here, and I've got files in my Doodle folder, which are all on my GitHub repo, and we can see what's in here. And all these files are typical files that you might find in a project. And if you look at these files, if we open a typical C file, we can see, what we expect, normal C file. But we can also open a binary file. So this binary file is nothing interesting. And if we look at it, we don't see much of interest. Now, this particular file is just junk. I just made it up, but this is what it would look like if you opened any compiled file. But we can have a look at a binary file, and so this is what's in there. If we can change it, it's written in hex, so we have from 1, 2, 3 all the way up to 10 is written as A, 11 is B, all the way up to 15 is F. So a 1 and a 0. So nothing terribly interesting about that, and we'll look at this more probably in a few months from now when we finally look at these kinds of files and how they work. When we talk about files in Linux, there are a few concepts that help us understand a little bit about how Linux looks at files. So if you've spent any time poking around Linux or being interested in Linux or Unix in general, you would have heard that everything is a file, from files to directories to sockets and all sorts of things are viewed by the Linux kernel as files. And files are identified by the Linux kernel by something called an inode. So the inode, essentially you can think of it as a table of all the files with some metadata about them. When you look at a file in Linux, normally on the command line, we're familiar with the ls command that just shows us where, what's in a particular directory. But we can also see the inode numbers with .i. So let me go into a directory with fewer files so that we can see it. That's the normal ls. And if we do .i, that gives us the number that is associated with the inode of each file. So every file in your system and everything that Linux considers a file has an inode number. So we can see here, each of these two files have an inode. And if we look at we can look at the Linux kernel. This is fairly recent. the FS directory, you may know, is the file system directory, and this has everything about file systems. So on this machine, the file system is called ext4, which is the most common file system on the Linux on Linux machines. And you can see there's quite a bunch of files that help us set up the file system. And if we just look in these files for inode, we can see that there's quite a ton of places that inode is used. So it's pretty significant in the Linux kernel. If we look here, inode, throughout all these files, inodes are used all over the place. So inodes have metadata about your file. They tell the system what type of file it is, if it's a regular file, a directory. So directories are also files. It tells it gives permissions. So when you do an ls-l and you get these permissions, they are assigned in the inode. It also gives the owner, the group, all this information that you get from ls-l is in the inode. And we can do stat, and we can see information about that file. We can see that this file was created then, and whenever it was modified and so on, who owns it, and all that kind of thing. So that's the inode. So you can think of the inode as the way that the Linux kernel maps your whole view of your hard drive, and looking at all the files that you have. But aside from inodes, another concept that's important in terms of files when we're working with them is the concept of file descriptors. So when we go to open a file in C or in any programming language, we're opening that file, and the operating system needs to know what we're doing. And so the way that it does that is with something called a file descriptor. So a file descriptor is just a number that's kept on a table of all the files that are opened by any particular process. So when we run our compiler, say, and we open our source file, that process, the compiler busy running, opening that source file, gets an entry into the file descriptor table of our source file. So let's start looking at some code. So I've got the main file here, which does open a file. So if we look at the code line by line, the file, this first line provides a file pointer. A file pointer is a pointer to a structure within the C standard library that gives us access to the mechanics of working with files. So the fopen, again using the word abstraction, is an abstraction to how the file, how the operating system is using, is working with files. So when we get a file, we're opening it. The file needs a file name, and it needs a flag as to what to do with it. So R means just read it. We can't write to the file. Since what we're opening is our source file, it's going to just be a read-only file. And then going down to the next few lines here, we're just handling any errors and getting out of the program if it fails. And then create some memory with malloc, so we get a chunk of memory from the operating system in order to read our words in, and then make sure that we get that memory, and then create a buffer, an array into which to put the words, and then we just read our words, and for now we're just gonna print them back out. This is closing the file back up again, and then we just print out our buffer, and then the memory that we got with malloc we free again, give it back to the operating system, and then we exit the file. So fairly simple, and just a bit of a start. So in this file, we said we will open a file called words and .txt. So if I open that file, just so we can see, it's just a few words. And if I compile the file, we can, we've created the binary a.out, and if we run it, it prints the words that were in the words file. So simple start. What this is lacking so far is the ability to read in the file name, and so I've written another piece of that before, so I'm just going to combine the two of them. So if I go into here, but then I also open another file that I already wrote before, and this is just a command line parsing thing, nothing particularly interesting. So let's just copy that in, and we can paste that in here. And now we can get at the file name. So if we go down to main here, we need all of this, and we can paste that into main. And now instead of words, we'll get our input file. So that's input, oops, file name, and our output file name for now we do nothing with. So if I just show you basically what we've done here, we look at the arguments that we get from the command line, starting from, we said I to 1 because the first argument is the name of the file that we're running. So all our command line arguments are from there on, and then argc is the count of how many arguments we have. And then I'm not doing any malloc with this one. We're just using in my compiler, I'm just setting them to a length of 20. That should be enough for a file name. And then check for the O flag. I'm not sure if this is the best way to do it. I'm sure as I go along. It's a long time since I've written a lot of C, so I'm sure some of the stuff will get better as I do it. But this is what I came up with. So I check for the see if any argument has an O flag, then I'm going to skip fetch the next one. So it's a little hard to explain like this, but I get the next one along, and then increment I, so that I don't pick up the next one in the for loop. And so that picks up the one that's dash a file name prepended with the name -o, and that's normally the file that we're going to have as our output file, which is months down the line before that's of much use. And then down here I'm just looking if there's a file with C and it's got a dot. I don't know if that's the right way to do it, but that's what I thought of. And then I string copy it and just use some pointers to return that back to. So these pointers have input file, have output file. I just give up when I've got all the arguments that I want. So if somebody ran the file with more arguments, it would just ignore them. It's not really raising enough errors, I guess, but I think it should work. So let's just see. I think for this I should do exit failure. And oops. You can see my fingers are not used to Vim right now. I used to use Vim almost exclusively, but these days I edit in an IDE most of the time, so not so used to it. Okay, I'm not sure if that's going to work, but let's see. So it's going to, let's just do GCC. Args undeclared. Oh. That would help. Now we don't have a C file for us to run, so let's just move the Word file as if it's a C file. Doesn't matter that it's not, because we haven't got a compiler that works yet, so we can just try it. So a.out words.c, and it worked. We can give it a out file, .o words, and our out file would be words if that was a file that we had. So far it works. Our file reads a file and reads the command line arguments, gets the file name, opens the file, tells us what's in it, closes. So it doesn't do anything interesting yet, but that's the first step. So next week I'm going to get on to the next step where we start turning things into tokens. So most likely the first step is to turn one thing into a token, and I'll talk a bit about what tokens are in the context of a compiler, and then in the following week or weeks I'll work on getting as a good chunk of C.